This gives us the keys that we need to doing the homework assignment in terms of repeating the analysis several times with different standard deviations and then creating a graph of the standard error and slope versus those standard deviations. But our code can be a little bit more flexible than it is. And that's because right now we're doing what's called hard coding some numbers that don't have to be hard coded. And while it's not necessarily important right now, our code's working fine. One thing that we have to do, if suddenly we want to do more than 3, I believe in the homework I'm asking for 5 different standard deviations, there's several places where we have to change the code to make that work. So let me close this graphing window and scroll back up. Remember that this vector is 3 long. That's ultimately what's defining everything else that needs to be 3. But we're also telling it 3 times in order to create the space that we need it for the standard errors. We're also telling it to repeat our loop 3 times. If we want to go to 4, that means I'd have to change this to 4, I'd have to change this to 4, and I just have to change this to 4. Now that doesn't seem that bad, but it's also a little bit brittle way to code because I might forget all the places I need to change things, and this code isn't going to work, and I'll have to debug if I forget to change this in some place and it doesn't work. And that's really hard coding is one of the issues. One of the debugging issues, subtle debugging issues you might run into in R, is when you hard code things, you're creating situations where you might have a bug that's a little hard to find later. So how do I resolve this? Well, in this case, the information about how many times I need to repeat these values to create this vector and the number of times I need to go through my loop is information I already know after I've created this SDS. Because however long this SDS vector is something I can get at with code. If SDS is here, there are 3 values there. I can use a function called length, and length is a function that will tell you how many elements an atomic vector has. So I do a length on SDS, and it'll say there's 3. Now that's a convenient number because I can then go here and say, well, this needs to be the length of the SDS vector, this 3. So I'm no longer hard coding the 3. I'm putting in a length of SDS, so this times will be however long this vector is. And also I need to go through my loop however many times this, or however many elements this vector has. So again, I can replace that hard coded 3 with a length of SDS. So that's it. Now my code is robust. It will still work. I can run it. And it's still going to work with 3 values. We'll talk a little bit later about why this may not look like such a straight line. And let's say I want 4 values. So I'm going to add the value 2 to this list. So I'm going to do 0.1, 0.5, 1, and 2. All I need to do now that I've gotten rid of the hard coding of the 3s is change this vector and my code will still work. Because it'll just take the length here, which is now 4, and it'll take the length here 4. If I hit source, I will now have 4 points on my graph, representing the 4 different standard deviations at 0.1, 0.5, 1, and 2. So just a quick example of what the term hard coding means and why hard coding is sometimes not a very good practice in programming. In fact, it's frequently not a good practice in programming, because it can create things that you have to change that you don't remember that you have to change, which means if it does have to change and you've forgotten where to change it, that's a bug, and it can be a bug that's a little bit hard to find. So we now have some really flexible code for completing the homework assignment. You can put as many different standard deviations you want in this vector. I believe you asked for 5, but you can put 6, you can put 10, you could put as many as you want. And this will repeat as many times as you ask it to based on the length of that vector. But let's take a look at something. Each time I run this code, you'll see I'll get results that are a little bit different. And sometimes it'll look less like a line, and sometimes it'll look more like a line. In this case, these 3 look like they might be on the same line, but this one seems to be a bit off. If I run it again, I'll get something subtly different. In this case, this one's low again, but it's not as much as it was before. And here's one that's different. Now this one's higher than the line that you might see here and lower. And this one looks like it might be a little lower. The point here is every time it's going to be a little bit different. And sometimes it'll look like a super straight line, and sometimes it won't look like a line at all. Now, in order for this particular spread in standard deviations, I will really have to run this a lot of time to get the rare instance where it won't look like a line, because going from 0.1 to 2 is a pretty big spread. So it generally has an increasing trend anyway, and I haven't created an instance where it doesn't look like it's always increasing, or what we call monotonic. And I might have to do this a lot to generate that type of example. But the point is it's different every time, and that's because we're using what's called a stochastic method or a random method. Our estimate in the standard error is subject to the same uncertainties that we only have one realization of our error in our observations. So these points can be in a lot of different places on a vertical axis here, depending on the randomness of our particular observations that time through. And we can see what that means because now we've created this program that makes it really easy to rerun this as many times as we want based on the length of this vector. So let's go to that vector and let's go nuts. Let's say 500 values between 0.1 and 0.2. So we can use that seq function, the sequence function, and say I want to go from 0.1. I'm going to use the same range of values between 0.1 and 2. And I want to go to the value 2. And my length dot out, which is the argument that controls how many elements this vector will have when you use the seq function, is going to be 500. So I want you to, I'm telling the computer to space values evenly, 500 values evenly between 0.1 and 2 and create a vector for me. And that's going to be my standard deviations. Again, the computer, if it can do it once, it can do it 500 times, it can do it 5,000 times. That's the purpose of these loops. And I don't have to change anything else because I made this super flexible. The length of this vector controls everything else. So if I hit source, it'll take a little bit longer to run, that's 500 times, but it's still pretty fast, right? Less than, it might have taken a second. Now I have 500 different values, and you can see that scatter that I was talking about. Each one of these is just a single realization. It's going to be a little low or a little high based on the randomness that you have for each analysis, which is only 20 values representing your x and y or your independent and dependent variables. And you can see how under rare occasions, if I were to pick a number from this distribution at a value around here and I got a higher value, and I were to pick one over here and got one of these at the bottom end of this distribution and got a lower value, I may not even get a monotonic result. I might end up with a value that's high here and lower here. Remember, we had 1 and 2, so that's probably not going to happen because the highest values here at 1 are still higher than the lower values at 2. But it all depends on which values for standard deviations I pick. I might get something that doesn't look much like a straight line if I base it on just one realization of the error for each example that I'm picking to compare standard deviations to standard errors. So if you don't want that to be confusing, you want to pick a nice wide range of standard deviations when you create the errors, and that way you're much less likely to get this non-monotonic relationship that you should get, right? You should see a higher standard error in the slope if you give it a higher standard error deviation for that error. So that's something to keep in mind when you're doing stochastic analyses. It's a pretty common thing that might happen. You might want to repeat your analysis more than once and take the average of the results. That's really what Monte Carlo is all about. If you want to get a more stable estimate of the relationship between the standard deviation and the standard error. And we will talk much more about that later.